Imagine a city of stars so vast that if you counted one every second, it would take you over 6,000 years to count them all. That city is your home, the Milky Way galaxy. Tonight, we drift among the stars. There is no test at the end, no rush, no urgency, just the slow unfolding of cosmic truths to carry you gently into rest. The universe is vast beyond comprehension, yet tonight we focus on just one part, our home galaxy. Hundreds of billions of stars, trillions of planets, rivers of dark matter, clouds of gas and dust, and perhaps countless forms of life we have never imagined. All of this waiting to be whispered into the dark. Tonight, let's drift off together while exploring 100 soothing facts about the great spiral of stars that holds us gently in its arms. There's no rush here, no test at the end, just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I'm glad you found your way here tonight. Perhaps you've had a long day, or maybe you simply enjoy falling asleep to thoughts bigger than tomorrow. Either way, this journey is for you. There is something calming about contemplating the stars. They are so distant, so ancient, so indifferent to our small concerns, and yet they are our origins. The atoms in your body were forged in stellar cores billions of years ago. So settle in, let your breathing slow, and let the weight of the day drift away like stardust on a gentle wind. The Milky Way is a barred spiral galaxy, a swirling collection of stars, gas, dust, and something far more mysterious, dark matter. It stretches across 100,000 light-years from edge to edge, and somewhere within its gentle curve, on a small rocky world orbiting an ordinary yellow star, you exist. You are here, listening to these words while the galaxy slowly turns around you. Tonight, we will wander through its spiral arms. We will visit stellar nurseries where new suns are born. We will drift past ancient stars older than the Earth itself. And we will peer into the mysterious heart of the galaxy, where a supermassive black hole waits in silence. But there is no hurry. The galaxy has been here for over 13 billion years. It can wait a little longer while you rest. Let us begin with a truth so large it barely fits into the mind. The Milky Way is approximately 13.6 billion years old. It began forming not long after the universe itself was born. The universe itself is only about 400 million years older. Our galaxy is nearly as old as time. To put that in perspective, imagine the entire history of Earth compressed into a single day. In that day, the Milky Way would have existed for almost 3 full days before Earth even appeared. Our galaxy is ancient, far older than the ground beneath your feet or the air you breathe. And within this ancient spiral drift between 200 and 400 billion stars. That number is almost impossible to grasp. It means there are more stars in the Milky Way than grains of sand on many of Earth's beaches combined. If you tried to count them 1 star per second, it would take you over 6,000 years to reach just 200 billion, longer than recorded human history. each one a sun, some larger than ours, some smaller, many surrounded by worlds we have never seen. The Milky Way stretches across roughly 100,000 light-years, perhaps even more. A light-year is the distance that light travels in 1 year, and light moves fast, nearly 300,000 kilometers every single second. That is almost 10 trillion kilometers in a single year, a number so large it escapes ordinary comprehension. So when we say the galaxy is 100,000 light-years wide, we are saying that even light itself, the fastest thing in the universe, would need 100,000 years to cross from one side to the other. If you turned on a flashlight at one edge of the Milky Way and waited for its beam to reach the other side, you would wait 100,000 years. Civilizations would rise and fall, ice ages would come and go, and still the light would travel. That is the scale of our home, measured not in meters, but in time. And yet, for all its width, the Milky Way is remarkably thin. The main disk of stars where our sun lives is only about 1,000 light-years thick. Imagine a record spinning in the dark, wide and flat, with a gentle bulge at the center. If the galaxy were the size of a dinner plate, the disk would be thinner than a sheet of paper. That is our galaxy. A vast, thin disk of stars rotating slowly through the endless night. Our solar system does not sit still within the galaxy. It orbits like a small boat, circling a vast, invisible center. The Sun and all its planets travel around the Milky Way at a speed of over 820,000 kilometers per hour. That is more than 200 kilometers every single second. Faster than any rocket, faster than anything humans have ever built. And yet, even at this tremendous speed, it takes our solar system approximately 225 million years to complete just one orbit around the galaxy. This is called a galactic year. One trip around the Milky Way, 225 million Earth years. A single lap in the slow, patient dance of cosmic time. In all its existence, our sun has made this journey fewer than 20 times. Think about what that means. The sun, our star, is about 4.6 billion years old, and in all that time, it has only circled the galaxy around 20 times. The last time Earth was in this exact position relative to the galactic center was during the late Triassic period. Dinosaurs were just beginning to dominate the land. They never saw the night sky you see now. The stars above them were different, the constellations unrecognizable. We have drifted slowly through different neighborhoods of the galaxy, and the stars around us today will not always be nearby. In another galactic year, the night sky will hold different lights, different patterns, different constellations. Everything is in motion, quietly, slowly, endlessly. Even as you rest, the Earth turns, the sun orbits, and the galaxy carries us gently forward through the dark. Now let us drift a little deeper into the structure of our home. The Milky Way is a spiral galaxy. From above, if you could somehow float far beyond its edges, you would see great curving arms sweeping outward from a glowing center. But here is something curious. We don't actually know how many spiral arms our galaxy has. It seems like something we should know about our own home, and yet the answer remains unclear. For decades, astronomers believed there were 4 major arms. More recent observations suggest perhaps fewer, or perhaps the arms twist and split in ways more complex than expected. Some models show 2 dominant arms with smaller spurs branching off. Others show a more complex web of structures winding outward from the center. The difficulty is that we're inside the galaxy. Trying to see its shape from within is like standing in a forest and trying to draw a map of the trees. Dust clouds obscure distant regions, stars blur into one another. The view is beautiful but incomplete. Here is something beautiful about the spiral arms. They are not solid structures. They are not rivers of stars flowing together in fixed paths. Instead, they are patterns, waves of density rippling slowly through the galactic disk. Imagine a traffic jam on a circular highway. Cars slow down as they enter the congestion and speed up as they leave. The jam itself stays in roughly the same place, even though different cars pass through it all the time. The spiral arms work in a similar way. Stars drift into these regions, linger for a while, and then drift out again. Our own solar system currently resides in a small structure called the Orion Spur. It is not one of the galaxy's grand spiral arms, but a minor branch, a quiet lane between larger highways, a peaceful corner of a vast and ancient city. When gas clouds pass through the spiral arms, something remarkable happens. The increased density compresses these clouds, and compression is the first step toward birth. Within these squeezed clouds, gravity takes hold, material collapses inward, temperatures rise, and eventually nuclear fusion ignites. A new star is born. This is why the spiral arms glow brighter than the space between them. They are lined with young, hot, blue-white stars freshly formed from the passing gas. The arms themselves are like cosmic nurseries, regions where creation happens again and again in slow, patient cycles. And the stars born there do not stay forever. They eventually drift away, moving on their own paths through the galaxy, while new stars take their place. The galaxy breathes in spirals. Now, let us turn our attention toward the heart of the galaxy. At the very center of the Milky Way, hidden behind curtains of dust and gas, lies something extraordinary, a supermassive black hole. It is called Sagittarius A star, named for the constellation in which it appears from our point of view on Earth. This black hole contains the mass of more than 4 million suns, all compressed into a region smaller than the orbit of Mercury. Its mass is staggering, and yet we cannot see it directly. We detect it only by its influence, by the way light bends around it, by the way stars orbit its invisible center. It is the anchor of the galaxy, a gravitational pivot around which everything else turns. You do not need to fear it. Its pull is strong, but we are far, far away, 26,000 light-years distant, safe in the outer reaches of the spiral. We cannot see it directly. Black holes emit no light. They are defined by what they do not release. But we know it is there. Astronomers have watched nearby stars whipping around an invisible point at tremendous speeds. Their orbits reveal the presence of something massive, something dark, something patient, the silent conductor at the galaxy's core. The stars nearest to Sagittarius A star move at astonishing speeds. One star, known simply as S2, completes its orbit around the black hole in just 16 years. At its closest approach, it travels at nearly 3% the speed of light. 3% of light speed. For a star, that is almost incomprehensible. Astronomers have tracked S2 for decades, watching it loop around the invisible center. Its motion is one of the strongest pieces of evidence for the black hole's existence. And yet, despite its immense gravity, the black hole at the center of our galaxy is remarkably quiet. It sleeps. Unlike the black holes in distant galaxies, which actively consume matter and blaze with light, Sagittarius A star is currently dormant. Occasionally, a wisp of gas drifts too close and flares briefly in X-rays as it spirals inward. But for now, The heart of the Milky Way rests in darkness, a sleeping giant surrounded by spinning stars. But it was not always so quiet.
There is evidence that long ago, the center of the Milky Way may have burned like a quasar. Quasars are among the brightest objects in the universe. They occur when supermassive black holes actively consume vast amounts of matter, releasing tremendous energy. When matter falls toward a black hole, it spirals inward, forming a disk. Friction heats this disk to millions of degrees, and it radiates across the electromagnetic spectrum, brighter than all the stars in the galaxy combined. If our galaxy once shone like this, it would have looked dramatically different, a spiral wrapped around a blinding heart of light. That time has passed, but echoes remain in the structures we can still observe. Around the black hole lies the central bulge of the galaxy, and when astronomers mapped this region, they discovered something unexpected. The bulge is not a smooth, round ball of stars. It is shaped like a peanut, swelling in the middle and narrowing at the ends like a twisting hourglass made of ancient light. At the heart of this peanut-shaped bulge lies another structure, a bar. The Milky Way is what astronomers call a barred spiral galaxy. This means that across its center runs an elongated stripe of stars, a kind of glowing bridge. About 2/3 of all spiral galaxies have bars. It is one of the most common structures in the universe, yet we did not confirm our own galaxy's bar until relatively recently. This bar rotates slowly, and its gravitational pull shapes the inner spiral arms. It stirs the gas, triggers new stars to form, and funnels material toward the black hole at the center. But that is not all. Deep within this bar, astronomers have found hints of another, smaller bar, tilted at a different angle, rotating independently. A bar within a bar, like nested gears turning slowly in the dark. The Milky Way's center is not one simple shape. It is a layered, shifting labyrinth of light and motion. And now, let us speak of something we cannot see. The galaxy holds together because of something invisible. By all logic, the Milky Way should not exist in its current form. Based on what we can measure, stars, gas, dust, the outer edges of the galaxy are spinning too fast. They should be flung into space, scattered like leaves in a storm, and yet they remain. This was one of the great puzzles of 20th century astronomy. Galaxies simply did not behave the way they should. The answer is dark matter. This mysterious substance does not shine, it does not reflect light, it does not emit any radiation we can detect, but it exerts gravity, and there is so much of it that it outweighs all the visible matter in the galaxy many times over. We do not know what dark matter is, but we know that without it, the Milky Way would fly apart. It is the invisible scaffolding holding everything in place. The rotation of the Milky Way defies classical physics. According to Newton's laws, stars farther from the galactic center should orbit more slowly, just as outer planets move more leisurely around the sun. But in the Milky Way, stars in the outer regions orbit almost as quickly as those near the center. This was deeply puzzling. For decades, astronomers could not explain it, until they considered that there must be more mass than we can see, an enormous halo of dark matter surrounding the entire galaxy, extending far beyond the visible stars. With dark matter, the mathematics work. The galaxy turns like a solid wheel, not because we understand it fully, but because something unseen is holding it in place. The galaxy spins on invisible threads. The dark matter halo is not a thin shell. It is a vast spherical cloud enveloping the entire galaxy. It extends far beyond the furthest visible stars.
Some estimates suggest it may reach hundreds of thousands of light-years in all directions. And here is a remarkable fact. Most of the Milky Way's visible stars lie within the flat, luminous disk, the spiral we picture when we imagine our galaxy. But the majority of the galaxy's mass resides elsewhere, in the dark matter halo, beyond the light, beyond the stars. When we think of the Milky Way, we picture its spiral arms and starry plane, but that is only the glowing surface. The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything like a quiet shroud. Let us now drift beyond the bright disk into the outer reaches of the galaxy. Beyond the spiral arms lies the galactic halo, a vast, nearly spherical region surrounding the disk like an invisible atmosphere. The halo is not empty. It contains ancient stars, globular clusters, and enormous amounts of dark matter. But its stars are spread thin, scattered across immense distances, orbiting in long, slow arcs that rarely touch the disk. Many of these halo stars are among the oldest in the galaxy. Some may have formed before the Milky Way's disk even existed. They carry the chemical fingerprints of a younger universe, a time when heavy elements were rare and the cosmos was still learning to create complexity. The halo is the galaxy's outer memory, quiet and dim but still in motion. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled. Their existence hints at an earlier time of star formation, a deeper history etched into the outer halo. They have burned for billions of years, slowly fading, carrying with them the quiet residue of a time when the Milky Way was still gathering its shape. The disk may be bright, but the halo remembers further back. The farthest stars in the galaxy orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light-years from the center.
These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant sentinels. They are faint, sparse, and far between, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not just what we see. It extends deep into the dark, shaped by wanderers at its edge. Scattered throughout the halo are more than 150 globular clusters. These are among the oldest objects in the galaxy, compact spheres made of hundreds of thousands of stars, all bound tightly together by gravity. They orbit the galactic center in the halo, like moths circling a distant flame, rising above the disk and falling below it in slow, patient loops. Many of these clusters are more than 12 billion years old. Some contain stars that predate the Milky Way itself. They formed when the universe was young, before the galaxy had fully taken shape, before the disk had settled, before the spiral arms had wound themselves into their current form. These quiet golden spheres drift patiently above and below the galactic plane, glowing softly in the dark. In astronomy, the word metal has a special meaning. It refers to any element heavier than helium. The earliest stars in the universe had almost none of these metals. They formed before earlier generations of stars had a chance to forge and scatter heavy elements. Today, astronomers seek out these metal-poor stars in the halo of the Milky Way. They are rare and faint, and incredibly old. One such star, discovered high above the galactic plane, may be nearly as old as the universe itself. It contains almost no heavy elements, a signature of stars born shortly after the Big Bang. It burns quietly now with a soft red glow, low in mass but rich in history. Not just a star, but a time capsule, a living relic from the universe's earliest dawn. And now let us turn from the old to the new, from ancient relics to places where stars are still being born. Scattered throughout the Milky Way's spiral arms are regions called stellar nurseries, vast clouds of gas and dust where new suns are slowly taking shape. These nurseries are places of quiet transformation, cold, dark, patient, waiting billions of years for the right conditions. These clouds are composed mostly of hydrogen, the simplest element, the most abundant material in the universe. And they are cold, chilled to just a few degrees above absolute zero. In the darkness between stars, heat is rare. Within these cold, quiet clouds, gravity begins to gather material. Small regions grow denser, they collapse inward, and as they collapse, they warm. Eventually, the pressure and temperature rise high enough for nuclear fusion to ignite, and a new star opens its eyes for the first time. The birth of a star is not a sudden flash. It is a slow process, unfolding over millions of years. These clouds where stars are born are called molecular clouds, or sometimes giant molecular clouds. And the word giant is fitting. Some of these clouds stretch across hundreds of light years, vast enough to contain the mass of millions of suns. Inside them, the temperature hovers just a few degrees above absolute zero. In this extreme cold, molecules can form. Hydrogen pairs up, carbon monoxide drifts, complex chains of atoms slowly build. But despite their size, they are difficult to see, not because they are faint, but because they are hidden. Dust, tiny grains of carbon and silicates mixed with the gas. These grains block visible light, scattering and absorbing it like a curtain drawn across a window. To peer inside these nurseries, astronomers use infrared telescopes. Infrared light can slip through the dust, revealing the warm glow of stars being born. Without infrared eyes, we would not know what happens inside these veiled ancient nurseries. Some stars rotate hundreds of times faster than the sun. Most stars spin, but some spin incredibly fast, completing a full rotation in just a few hours. These rapid rotators are often young, massive, and unstable, with equators that bulge from centrifugal force. A few reach such high speeds that they fling off material, forming glowing disks around themselves. The sun rotates once every 25 to 35 days, depending on latitude. But these fast-spinning stars rotate hundreds of times more quickly, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the dark. The Milky Way is no longer young. In its early days, stars formed at a furious pace. The galaxy was rich with gas. Clouds collapsed everywhere, and the spiral arms blazed with newborn light. But now, star formation has slowed. Much of the original gas has already been used, converted into stars or expelled by supernovae or locked away in remnants. Today, the Milky Way produces only about 3 new suns each year. Astronomers sometimes describe our galaxy as middle-aged, not old, not dying, but past its peak of youthful creation. It still glows with beauty. It still forms new stars, but more slowly now, more quietly. A galaxy settling into its long, quiet afternoon.
And now let us speak of endings. For stars do not live forever. Massive stars, those many times heavier than our sun, live fast and die violently. After only a few million years, they exhaust their fuel and collapse, and then they explode.
These explosions are called supernovae, and they are among the most powerful events in the universe. For a brief moment, a single dying star can outshine an entire galaxy. Billions of suns' worth of light compressed into weeks. If a supernova occurred close enough to Earth, we would see it in the daytime sky, a new star appearing where none was before, bright enough to cast shadows at night. Such events have happened before in human history. Ancient astronomers recorded guest stars appearing suddenly in the heavens. But supernovae are not just destruction, they are also creation. In the heart of a dying star, heavy elements are forged. Iron, nickel, gold, uranium, elements that cannot be made in ordinary stellar fusion. And in the explosion, these elements scatter across the galaxy. When a supernova erupts, it sends a shock wave racing outward through space. This wave carries the star's outer layers blasted apart at thousands of kilometers per second. Gas and dust and freshly forged elements spreading into the void. Over thousands of years, these expanding shells become supernova remnants, beautiful wispy structures glowing in X-rays and radio waves. The Crab Nebula is one such remnant, the tattered remains of a star that exploded in the year 1054. Chinese astronomers recorded it as a guest star, bright enough to see in daylight. Nearly 1,000 years later, the debris is still expanding, still glowing, a memorial written in light. And here is something remarkable. As these shock waves sweep through the galaxy, they compress nearby gas clouds, the same process that triggers star formation in the spiral arms. So the death of one star can ignite the birth of many others. Destruction and creation woven together, the galaxy recycling itself across billions of years, a cycle of endings and beginnings. Not all massive stars vanish entirely when they explode. Sometimes a dense core remains, crushed by gravity into something extraordinary, a neutron star. Neutron stars are among the strangest objects in the universe. They contain the mass of 1 or 2 suns compressed into a sphere only about 20 kilometers across. A single teaspoon of neutron star material would weigh about 1 billion tons. Their gravity is so intense that the surface curves space-time dramatically. Time itself runs slightly slower on a neutron star than it does on Earth. Their magnetic fields are trillions of times stronger than Earth's, strong enough to rip apart atoms, strong enough to shape the space around them. And many of these neutron stars spin incredibly fast. Some complete dozens or even hundreds of rotations every single second. As they spin, they sweep beams of radiation across the galaxy like cosmic lighthouses. Astronomers call them pulsars. When a pulsar's beam happens to sweep past Earth, we detect a flash, then another, perfectly timed. Their pulses are so regular, so precise, that they rival atomic clocks, tiny spinning corpses keeping perfect time. Sometimes neutron stars come in pairs, 2 dense remnants orbiting each other, spiraling slowly inward. Their mutual gravity drains energy from their orbit. Each year they drift slightly closer. The dance quickens. And eventually, after millions or billions of years, they collide. These collisions are cataclysmic. They release vast amounts of energy and send ripples through the fabric of space itself. Gravitational waves. But the collisions also create something else, something precious.
In the violent merging of two neutron stars, conditions become extreme enough to forge the heaviest elements in nature: gold, platinum, uranium. The gold in your wedding ring, the platinum in a catalytic converter, the uranium that powers nuclear reactors. All of it created in moments of cosmic violence. Neutron star collisions, scattered through the galaxy, eventually gathered into planets, and eventually worn on human fingers or built into human machines. Much of the gold on Earth, the gold in wedding rings and ancient coins, in the circuits of your devices, was likely born in a neutron star collision. Forged in cosmic violence billions of years ago, scattered through space, and eventually gathered into our world. Many stars in the galaxy live in pairs, orbiting each other in gravitational embrace. These are called binary stars. But even this bond can be broken. If a binary system passes close to the Milky Way's central black hole or through a dense cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is hurled out of the galaxy entirely, becoming a rogue star, speeding through intergalactic space. These stellar breakups happen silently, in places we rarely see, a quiet tearing of ancient partnerships by gravity's indifferent hand. Star clusters, too, can dissolve into the galactic field. Many stars are born not in isolation, but in groups, tight clusters formed from the same collapsing gas cloud. These clusters, bound by mutual gravity, drift together for millions or even billions of years, but over time they begin to scatter. Tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics all work to pull clusters apart. Stars peel away one by one until the cluster fades into the general star field of the galaxy. Even our Sun was likely born in a stellar cluster long ago, its siblings now scattered, dimmed, or lost in the haze of distance. Let us now consider something surprising. The Milky Way has not always looked the way it does today, and its history is not one of quiet isolation. Our galaxy has collided with other galaxies multiple times. This may sound violent, and in a sense it is, but these are slow collisions, unfolding over hundreds of millions of years, not the crashes of everyday life. These were not gentle encounters, they were cosmic mergers lasting hundreds of millions of years, smaller galaxies drawn in by the Milky Way's gravity, stretched, torn, and absorbed. One such collision is happening right now. A small galaxy called the Sagittarius Dwarf is being pulled apart as we speak. Its stars are streaming into the Milky Way, wrapping around our galaxy in long, looping arcs. It has already passed through our disk several times, and each passage strips away more of its stars. A galaxy slowly dissolving into our own. But the Sagittarius Dwarf is not the largest galaxy the Milky Way has consumed. About 10 billion years ago, a much larger collision occurred. A galaxy roughly the size of the small Magellanic Cloud merged with the early Milky Way. Astronomers call it Gaia Enceladus, or sometimes the Gaia Sausage, because of the shape its stars trace in certain diagrams. This collision was significant. It reshaped the young Milky Way, thickening its disk and scattering stars into the halo. Many of the stars we see today in the inner halo are not native to the Milky Way. They are immigrants, survivors of a galaxy that no longer exists. The Milky Way grew by absorbing others. It is in part a collection of former neighbors. The evidence of these ancient collisions is still visible. Scattered through the halo are long, thin ribbons of stars called stellar streams. These are the stretched-out remains of galaxies and star clusters that were torn apart by tidal forces. They wrap around the Milky Way like ghostly threads, each stream a memory of something that once existed and no longer does. Just as the moon's gravity pulls tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, even globular groups feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, drawing out long stellar streams or peeling stars away from their orbits.
Many of the faint arcs of stars mapped across the sky are remnants of such encounters. Clusters in the process of being unraveled, galaxies slowly torn apart. The galaxy doesn't break these structures suddenly. It unravels them patiently, strand by strand, over millions of years. And here is something curious. Some stars in the Milky Way orbit in the wrong direction. While most stars follow the galaxy's general rotation, these retrograde stars move against the flow. They are likely foreigners, stars that were born in other galaxies and captured during ancient mergers. They still carry the momentum of their former homes, orbiting backward through a galaxy that is not their birthplace. But the story of galactic collisions is not over. The Milky Way's greatest encounter lies ahead. Approaching us at roughly 400 kilometers per second is the Andromeda Galaxy, our nearest large neighbor, a spiral even larger than our own. Andromeda is about 2.5 million light-years away, close enough that on dark nights you can see it with the naked eye, a faint smudge of light in the constellation of the same name. If you live in the northern hemisphere, step outside on a clear autumn evening. Look toward the constellation Andromeda, and there it is, the most distant object visible to the unaided human eye. Photons that left that galaxy 2.5 million years ago are entering your eye. Light that began its journey when our ancestors were still learning to walk upright. And it is moving toward us. In about 4 to 5 billion years, the two galaxies will meet. Their outer halos will begin to brush against each other. Stars will be thrown into new orbits. Gas will collide and compress. A new chapter in the story of our galaxy will begin. But here is something reassuring. When galaxies collide, the stars within them almost never touch. This may seem strange, two vast spirals containing hundreds of billions of stars passing through each other. Surely there must be countless impacts. But the distances between stars are so immense that direct collisions are extraordinarily rare. The stars will simply glide past one another like dancers in a crowded hall. What will change is the shape of the galaxy. The spiral arms will be disrupted, the disks will merge, gas will be compressed, igniting new bursts of star formation. Over billions of years, the two spirals will blend into something new. Astronomers have already given it a name, Milk Cometa, or sometimes Milkdromeda, a new galaxy born from two. The Milky Way does not drift alone through the universe. It belongs to a family. Astronomers call it the Local Group, a collection of more than 50 galaxies bound together by gravity, spanning roughly 10 million light-years. Most of these galaxies are small, dim, easily overlooked, but together they form a gravitational community drifting through the expanding universe as one. The Milky Way and Andromeda are the two largest members, the gravitational giants around which everything else orbits. The smaller members are mostly dwarf galaxies, tiny collections of stars, some containing only a few million suns, dim and diffuse, easily overlooked. Many orbit the Milky Way directly, satellites circling their parent galaxy like moons around a planet. Others drift between the major spirals, caught in a gravitational dance that has lasted billions of years. A quiet neighborhood in an expanding cosmos. Among the Milky Way's closest companions are two irregular galaxies visible from the southern hemisphere, the Large Magellanic Cloud and the Small Magellanic Cloud. They appear as faint smudges of light detached from the main band of the Milky Way. Early observers mistook them for clouds, hence their name. But they are galaxies in their own right. The Large Magellanic Cloud contains about 30 billion stars. The small, perhaps 3 billion. They're visible to the naked eye from the southern hemisphere, faint patches of light that have guided sailors and inspired storytellers for millennia. For a long time, astronomers assumed they had been orbiting the Milky Way for billions of years. But recent measurements suggest they may be newcomers, perhaps on their first approach or their second. Visitors only recently captured by our galaxy's gravity, still learning the shape of their new home. As the Magellanic Clouds move through space, they leave a trail behind them, a long, thin stream of hydrogen gas stretching across more than half the sky. Astronomers call it the Magellanic Stream. This gas was stripped from the clouds by tidal forces and the Milky Way's own gravity. It traces their path through space like smoke from a passing aircraft. Eventually, this gas will fall into the Milky Way, fuel for future generations of stars. And here is something interesting. For many years, astronomers believed that Andromeda was the more massive galaxy, but recent studies, including measurements of the Magellanic Cloud's motion, suggest the Milky Way may be heavier. The question is not yet settled, but it is possible that our home galaxy is the giant of the local group. Let us now return to the shape of our galaxy. When we imagine the Milky Way, we often picture a flat disk, a perfect spiral spinning like a record. But the reality is more complicated. The disk of the Milky Way is warped, bent like a vinyl record left in the sun. This was discovered decades ago, but only recently have we understood how pronounced the warp really is. On one side, the outer edge curves upward away from the galactic plane. On the opposite side, it dips downward. This warping may have been caused by gravitational interactions with neighboring galaxies, the tug of the Magellanic Clouds, or ancient collisions with now dissolved satellites. Or perhaps the dark matter halo itself is slightly tilted, pulling the disk out of alignment. Whatever the cause, our galaxy is not flat. It ripples gently at its edges. And though many diagrams show it as a neat, even spiral, the Milky Way is not perfectly symmetrical. One side of the disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. The warp in the outer disk is lopsided. Even the star counts between hemispheres are slightly off. These asymmetries may be caused by gravitational encounters, past mergers, or the influence of dark matter. They remind us that galaxies, like living things, carry traces of their histories in their shapes, scars of collisions, wrinkles of time, and quirks of uneven growth that give them character and depth. The Milky Way's disk is not a single uniform layer. It has two components, a thin disk and a thick disk. The thin disk is where most of the young stars live, the spiral arms, the stellar nurseries, the familiar glow of the Milky Way across the night sky. It is relatively flat, perhaps 1,000 light-years thick, and it rotates smoothly in neat circular orbits. But surrounding this is the thick disk, a more diffuse layer extending further above and below the galactic plane. The thick disk is older. Its stars move on more chaotic paths. They bob up and down as they orbit. Two disks nested within each other, one young and orderly, one ancient and restless. Layers of time stacked in light. As the Milky Way rotates, it does not spin perfectly still. It wobbles. The disk slowly precesses like a spinning top that isn't quite balanced, shifting gently over millions of years. This motion may be caused by gravitational tugs from satellite galaxies,
or by asymmetries in the dark matter halo. The galaxy is not perfectly balanced. And here is something humbling. Despite all our measurements, we still do not know exactly how massive the Milky Way is. Estimates range from about 1 trillion to 2 trillion solar masses, including all the dark matter we cannot see. That is a factor of 2 of uncertainty for our own home, the place where we live. The galaxy still holds secrets, even from those who live inside it. Let us now consider where we are within all of this. Our solar system lies in the thin disk, about 26,000 light-years from the galactic center, roughly halfway out, not near the crowded core, not at the sparse edge, somewhere in between. And our position may be special. We orbit near something called the co-rotation radius. This is the distance where stars orbit at roughly the same speed as the spiral arms itself. Stars closer to the center overtake the spiral arms. Stars farther out lag behind. But near the co-rotation radius, stars stay with the pattern for longer. This may reduce how often our solar system passes through the dense, turbulent spiral arms. A quieter orbit, a safer journey, perhaps a good place for life. As our solar system orbits the galaxy, it does not travel in a perfectly flat circle. It bobs. Up and down through the galactic plane, like a horse on a carousel, rising and falling as it goes around. The Sun crosses the midplane roughly every 30 to 35 million years, drifting above, then below, then above again. Some scientists have speculated that these crossings might correlate with events on Earth, increased cosmic ray exposure or gravitational disturbances, but this remains uncertain. What we do know is that the Milky Way's disk is tilted relative to our solar system by about 60 degrees. The plane of the planets and the plane of the galaxy do not align. We orbit the Sun at an angle to our orbit around the galaxy. The Sun was not born alone. About 4.5 billion years ago, our star formed inside a molecular cloud along with hundreds, perhaps thousands of other stars. A stellar nursery, a cluster of siblings born from the same cloud of gas and dust. But that cluster has long since dispersed. The stars drifted apart over billions of years, pulled by the tides of the galaxy. Somewhere out there, scattered across the Milky Way, are the Sun's siblings, stars that share the same chemical fingerprints, the same birthplace, the same origin. Astronomers have tried to find them. A few candidates have been identified based on their composition and motion, but most remain unknown. Lost siblings wandering through the galaxy, unaware of their distant kin. Between the stars lies something vast and often overlooked: the interstellar medium. We think of space as empty, a vacuum, nothing but darkness between the points of light. But that is not quite true. The space between stars is filled with gas and dust, incredibly thin by any earthly standard, but present. If you could somehow gather all the gas in a cubic light-year of interstellar space, you might collect enough to fill a small balloon. On average, there is about 1 atom per cubic centimeter in interstellar space. Compare that to the air you breathe, which contains about 10 to the 19th power atoms per cubic centimeter. So, yes, it is sparse. But over tens of thousands of light years, even this thin material adds up. And within this emptiness, complex chemistry occurs. Molecules form on the surface of dust grains. Ultraviolet light drives reactions. The seeds of future stars and planets slowly gather. The interstellar medium is the raw material from which new stars are born, and it is shaped by the stars that came before. Supernovae do more than scatter elements, they also shape the space around them. When a massive star explodes, it carves out a bubble in the interstellar medium, a hollow region filled with hot, low-density gas. Some of these bubbles grow enormous,
And when they break through the disk, they create structures called galactic chimneys. Hot gas rushes upward out of the plane into the halo above. It rises, cools, and eventually falls back down. Astronomers call this the galactic fountain, material cycling up and down between the disk and the halo in a slow, continuous loop, driven by the deaths of stars. The cycle takes millions of years. Gas rises, cools, condenses into clouds, and eventually falls back down to form new stars. It is like watching breath in the cold, an invisible exhalation made visible only when it slows and condenses. The galaxy breathes through explosions, exhaling into the halo and inhaling once more. Right now, as you listen to these words, particles are passing through you.
Cosmic rays. High-energy particles racing through the galaxy at nearly the speed of light. Most come from supernovae, some from distant black holes, some from the sun. They strike our atmosphere constantly, showering down in invisible cascades. Every second, billions of these particles rain down on Earth. Most are blocked by the atmosphere, but some make it through, passing through your body without you ever knowing. They carry energy from across the galaxy, messages from distant explosions that happened thousands or millions of years ago. But cosmic rays are not alone. Every second, trillions of neutrinos pass through your body, ghostly particles with almost no mass and almost no interaction with matter. They were born in the hearts of stars, in supernovae, in the Big Bang itself. They pass through planets, through stars, through entire galaxies without stopping. The galaxy is filled with invisible messengers we barely know exist. The Milky Way is wrapped in invisible lines, magnetic field lines. We cannot see them, but they are there, threading through the entire galaxy like a vast invisible web. The galactic magnetic field is weak, far weaker than a refrigerator magnet, but it stretches across tens of thousands of light years, and it shapes what happens in the space between stars. Tiny dust grains align themselves along the magnetic field. They spin and orient like microscopic compasses pointing along the invisible lines. This alignment polarizes the light passing through, and by studying that polarization, astronomers can map the shape of the galactic magnetic field, an invisible force revealed through specks of dust. The galactic magnetic field does more than align dust, it guides cosmic rays.
Cosmic rays are particles, mostly protons, traveling at nearly the speed of light. They come from supernova explosions, from distant galaxies, from the most violent events in the universe. When these particles enter the Milky Way, they do not travel in straight lines. The magnetic field bends their paths, curves them, spirals them around the field lines. This is why we cannot trace cosmic rays back to their sources. The magnetic field scrambles their directions like a maze with no clear exit. To map this invisible structure, astronomers use radio waves. Certain radio emissions, called synchrotron radiation, reveal where the magnetic field is strongest, the galaxy's magnetic skeleton, traced in radio light. And now, let us speak of something truly extraordinary. Above and below the galactic center rise two enormous structures. They are called the Fermi bubbles. Discovered in 2010, these bubbles are made of gamma rays, the highest energy form of light. They extend roughly 25,000 light years in each direction, above the center and below it, like twin balloons inflating from the heart of the Milky Way. They are invisible to the naked eye, invisible even to most telescopes. Only specialized instruments sensitive to gamma rays can detect them.
Their discovery was a surprise. No one expected such enormous structures hiding in plain sight. And yet they are there, towering above and below the galaxy like ghostly wings we never knew we had. What created the Fermi bubbles remains a mystery. One possibility is that the supermassive black hole at the center was once more active. Perhaps millions of years ago, it consumed a large amount of matter and released jets of energy. Those jets may have inflated the bubbles like a cosmic breath blown outward into the halo. Another possibility is intense star formation near the galactic center. A burst of supernovae all exploding in a relatively short time could have produced enough energy to create such structures. We do not know for certain.
But the bubbles remind us that the galaxy we live in is not fully mapped. There are features hidden in frequencies we cannot naturally see, waiting to be discovered. Let us now meet some unusual travelers. Most stars in the Milky Way follow orderly paths. They orbit the galactic center in predictable loops for billions of years. But some stars are different. They move at extraordinary speeds, fast enough to escape the galaxy entirely. These are called hypervelocity stars. They move so fast that the galaxy's gravity cannot hold them. They are leaving, never to return. How does a star reach such speeds? The most common explanation involves the supermassive black hole. When a binary star system wanders too close, one star may be captured while the other is flung outward like a stone from a sling. The black hole's immense gravity provides the kick, and the ejected star rockets away at thousands of kilometers per second. Some travel at over 1,000,000 kilometers per hour, racing toward the edge of everything we know. Runaways fleeing into the dark. Some hypervelocity stars will eventually leave the Milky Way forever. They will drift out of the halo, beyond the reach of our galaxy's gravity, and sail into intergalactic space, alone. Astronomers have observed such stars heading outward. Their trajectories point away from the Milky Way with no return. And there are others, rogue stars, stars that wander without any companions, perhaps ejected from clusters or torn from binary systems long ago. They travel the galaxy in solitary orbits, no planets, no siblings, just a single star moving through the dark. Imagine a sun with no one watching its light, no planets to warm, no life to illuminate, just a glow in the emptiness. The Milky Way is home to countless such wanderers, drifting alone through an ocean of night. And while some stars leave, others arrive. Astronomers have identified stars in the Milky Way that were born in other galaxies. They came here during ancient collisions. When smaller galaxies merged with our own, their stars were absorbed and now orbit alongside native stars. These immigrant stars are indistinguishable by appearance. They shine just like any other star. They follow similar orbits. But how do we know which stars are immigrants? Chemistry. Each star carries a chemical fingerprint. The specific mixture of elements reflects the environment where it formed. Stars born in smaller galaxies often have different ratios of elements than those born in the Milky Way. Lower amounts of certain metals, different isotope signatures. By reading these fingerprints, astronomers can trace where a star came from even billions of years later. Strangers revealed by their composition. Some of the oldest objects in the universe live inside our galaxy.
stars that formed shortly after the Big Bang. The universe is roughly 13.8 billion years old, and some stars in the Milky Way are nearly that ancient, 13 billion years old or more. They were born when the cosmos was young, when the first generation of stars was still lighting up a dark and formless universe. These primordial stars saw galaxies take shape. They witnessed mergers, collisions, the birth of billions of suns. They were here before Earth, before the Sun, before the solar system even began to form. And they are still burning. Small, red, and dim, they conserve their fuel over immense timescales, living quietly for longer than our galaxy has existed. Fossils of light in a changing sky. The oldest stars have a distinctive signature. They are poor in metals.
Remember, in astronomy, metal means any element heavier than helium. Iron, carbon, oxygen, all metals by this definition. These elements were not present in the early universe. They had to be forged inside stars and scattered by supernovae. So stars that formed before many supernovae had occurred contain almost no metals. They are called hypermetal-poor stars. They preserve the conditions of the early cosmos. Their composition reflects what the universe was like 13 billion years ago. Studying them is like reading a letter from the past, written in starlight and preserved across cosmic time. And now, let us consider the worlds that orbit these stars. For most of human history, we did not know whether other planets existed beyond our solar system. We suspected they might, but we had no proof. That changed in 1995. The first exoplanet orbiting a sun-like star was confirmed, and since then, thousands more have been found. The floodgates opened, planet after planet revealed by tiny wobbles in starlight, by dips in brightness, by direct imaging. Astronomers now estimate that the Milky Way contains hundreds of billions of planets. On average, every star in the galaxy has at least one planet. Many have several, some have more than 10. The galaxy is not just a sea of stars, it is a sea of worlds, rocky planets, gas giants, ice worlds, and types we have yet to name. But not all planets orbit stars. Some drift alone through the darkness between star systems, worlds without suns. They are called rogue planets, dark wanderers drifting between the stars. No sunrise, no sunset, just endless night. How do they form? Some were ejected from their birth systems by gravitational encounters, flung out into interstellar space. Others may have formed directly from collapsing gas clouds without ever having a parent star.
Astronomers believe there may be billions of rogue planets in the Milky Way, perhaps more rogue planets than stars. They are difficult to detect, dark worlds emitting no light of their own, visible only when they pass in front of distant stars. Lonely wanderers in a galaxy full of light. Not all regions of the galaxy may be equally hospitable for life. Astronomers have proposed the concept of a galactic habitable zone, a ring-shaped region where conditions might favor the emergence of life. Not too hot, not too cold, not too crowded, not too sparse. Too close to the center and the environment is harsh, dense stellar populations, frequent supernovae, intense radiation, not ideal for the long-term stability life requires. Too far out and the heavy elements become sparse. Fewer metals means fewer rocky planets and less raw material for complex chemistry. The sweet spot lies somewhere in between, and our solar system appears to be in it. Perhaps that is not a coincidence. Perhaps we are here because this is where life can be. A quiet region with enough heavy elements and enough distance from danger for life to take hold. Life requires ingredients: carbon, hydrogen, oxygen, nitrogen, the building blocks of proteins and DNA. And here is something remarkable. These building blocks exist throughout the galaxy, not just on planets. They drift in interstellar space, clinging to tiny grains of dust. Astronomers have detected complex organic molecules in molecular clouds, amino acid precursors, sugars, carbon chains. The ingredients for life are not rare. They are scattered across the galaxy in the cold, dark spaces between stars. They form in the chemistry of clouds, shielded from starlight, where reactions can proceed slowly over millions of years. The galaxy brews the seeds of life in silence.
Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and more. Though not alive, they are chemically rich, formed in the atmospheres of dying stars or within cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into the gas that forms stars and planets. Some may have fallen onto the early Earth. The galaxy's dust is not just debris, it is a cargo of potential, drifting silently through the dark. These interstellar molecules do not stay in space forever. When new solar systems form, the surrounding gas and dust collapse inward, and with them come the organic compounds that had been drifting between stars. They become part of comets, part of asteroids, part of the raw material from which planets are built. And then, through impacts, they are delivered to the surfaces of young worlds. This may have happened on Earth, comets and meteorites carrying organic molecules raining down on our planet billions of years ago. The ingredients for the first life may have arrived from the stars, a delivery across light years. Let us now consider what we can see and what we cannot. When you look up on a clear, dark night away from city lights, you see the Milky Way, a pale band of light stretching across the sky. It is beautiful, but it is also a tiny fraction of what is there. With the naked eye, you can see perhaps a few thousand stars, maybe 6,000 under perfect conditions. That is roughly 0.00003% of the stars in the galaxy, a vanishingly small sample. The rest are too faint, too distant, or hidden behind clouds of dust. What we see with our eyes is a glimpse, a window onto a vast, unseen ocean. Because we live within the galaxy, we cannot look down on it from above. Instead, we see it from the inside, a flat ribbon of stars stretching across the sky, curved only by the horizon. This edge-on view compresses the galaxy into a single arc, making it hard to grasp its full structure from our perspective. It took centuries of observation, cataloging, and mathematical deduction to realize the spiral we belong to. From Earth, we gaze through its disk, like standing in a forest and looking along the line of the trees. We do not see the shape we are part of, only the vastness that surrounds us.
The galactic plane marks a dense path of stars. If you look up on a dark night away from city lights, you may see a hazy river of starlight crossing the sky. That is the galactic plane, the thickest slice of the Milky Way's disk. It is not a line, but a depth, a vast flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point, we are looking along the grain of the galaxy, peering through its richest corridors. This band is not just beautiful, it is the crowded, humming heart of where most stars live and die. One of the great challenges of studying the Milky Way is that we are inside it. We cannot step outside and photograph the galaxy from above. We must infer its shape from the view within. Imagine trying to map a forest while standing among the trees. You can see nearby trunks clearly, but the distant edge is hidden by everything in between. The same is true for the Milky Way. Interstellar dust blocks our view. It absorbs and scatters visible light, creating dark lanes and obscuring distant regions. The galactic center lies in the direction of Sagittarius, but we cannot see it with ordinary telescopes. Too much dust stands in the way. The galaxy hides much of itself from its own inhabitants. If you look toward Sagittarius on a summer night, you are looking toward the heart of the galaxy. The Milky Way appears brightest in this direction. More stars, more light, more depth. But even at its brightest, the center remains hidden, buried behind 26,000 light-years of gas and dust. The supermassive black hole Sagittarius A star is invisible to the naked eye, invisible even to ordinary optical telescopes. We know it is there only through other wavelengths: radio, infrared, X-ray, frequencies that can pierce the veil. The brightest region of the sky conceals the most mysterious, a hidden heart beating in darkness. But we have learned to see in other ways. The human eye perceives only visible light, a narrow slice of the electromagnetic spectrum, but the universe speaks in many frequencies: radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. Each reveals something different about the galaxy. Radio telescopes detect cold hydrogen gas spread across the disk. They can trace the spiral arms even through the dust. Infrared telescopes peer through clouds that block visible light. They see warm dust and stars forming inside dense nebulae. With infrared eyes, we have photographed the very center of the galaxy. X-ray telescopes reveal the violent side of the galaxy. Hot gas heated to millions of degrees emits X-rays. So do supernova remnants and the regions around black holes. With X-ray vision, we can see the Fermi bubbles and trace the aftermath of cosmic explosions. And then there are the distance markers. Certain stars, called Cepheid variables, pulse with a regular rhythm. Their brightness rises and falls over days or weeks. And here is the key: the period of their pulsation is directly related to their true brightness. By comparing how bright they appear to how bright they truly are, astronomers can calculate how far away they are. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the dark, blinking beacons scattered through the spiral. Astronomers map the galaxy using these variable stars. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars, and some types, like Cepheids and RR Lyrae, have well-known relationships between their brightness and their pulse period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity, and by comparing that to how bright it appears, its distance. Cosmic rulers made of light. In recent years, our understanding of the galaxy has been transformed by a single spacecraft, Gaia. Launched in 2013 by the European Space Agency, Gaia has been mapping the Milky Way with unprecedented precision. It has measured the positions and motions of nearly 2 billion stars. 2 billion! For each of these stars, Gaia has recorded where it is, how fast it is moving, and in which direction. Gaia orbits the Sun about 1.5 million kilometers from Earth at a special point called L2, where it can stare into the galaxy without Earth blocking its view. Year after year, it builds the most detailed map of the Milky Way ever made. This is the most detailed map of our galaxy ever created, a census of stars that would have seemed impossible just a few decades ago. And with this data, astronomers have uncovered secrets hidden for billions of years. Gaia's data has revealed the galaxy's hidden history. By tracking the motion of stars, astronomers have identified dozens of stellar streams, ribbons of stars that once belonged to smaller galaxies, now absorbed into the Milky Way. The Gaia-Enceladus collision we spoke of earlier was confirmed using Gaia data. Astronomers could see which stars moved together and trace them back to a common origin. Gaia has also given us a three-dimensional view of the galaxy's structure. The warp in the disk, the thickness of the spiral arms, the motion of the bar, all measured with extraordinary accuracy. Before Gaia, we knew the rough shape of our galaxy. After Gaia, we know its details, the wrinkles, the ripples, the hidden streams. We are finally seeing our home galaxy as it truly is. There is another way to sense the galaxy, not with light, but with something more subtle, ripples in the fabric of space itself, gravitational waves. Predicted by Einstein over a century ago, these waves were first detected in 2015 by instruments called LIGO and later Virgo. Their detection was a triumph of physics, decades of effort, billions of dollars, and the most precise measurements humans have ever made. Gravitational waves are produced when massive objects accelerate violently, when black holes merge, when neutron stars collide. The waves spread outward at the speed of light, stretching and squeezing space by infinitesimal amounts. They pass through planets, through stars, through entire galaxies, carrying information about cataclysms billions of light years away. Right now, as you rest, gravitational waves are passing through you. You cannot feel them. The distortions are far too small, a fraction of the width of a proton. But they are there. Waves from black hole mergers in distant galaxies, waves from neutron star collisions that occurred before our solar system existed. Space itself is vibrating, subtly, constantly, a cosmic hum too faint to hear, but real. With gravitational wave detectors, we have opened a new window onto the universe, a way to listen to events we could never see. Before gravitational waves, we could only observe the universe through light. Now we can feel it trembling. This is a new era of astronomy, one that began only in 2015. We are just beginning to explore what we can learn. The universe speaks in trembling space, and we are just learning to hear. The Milky Way is not static. It is changing, growing, evolving, even now as you listen. Every moment brings subtle shifts. Stars drift, gas flows, dark matter halos slowly adjust. The spiral pattern winds and unwinds on timescales we can barely imagine. The galaxy continues to grow by accumulating matter from the space around it. Streams of gas flow in from the cosmic web, the vast network of filaments that connects galaxies across the universe. This web is invisible to ordinary telescopes, but it is there. Threads of dark matter and gas stretching between galaxy clusters, a scaffold on which the universe hangs. This inflowing gas provides fresh fuel for star formation. Without it, the galaxy would slowly exhaust its supply of raw material. And the mergers continue, small satellite galaxies still falling in, still being absorbed. The Milky Way has been growing for nearly 14 billion years, and it is not finished yet. Over billions of years, the structure of the galaxy shifts and changes. The spiral arms are not permanent features. They wind and unwind, they merge and split, they brighten and fade as waves of star formation pass through them. The bar at the center rotates slowly. Its shape and orientation change over hundreds of millions of years. Even the disk itself warps and flexes in response to gravitational forces. If you could watch the galaxy sped up 1 billion times, you would see it breathe, pulse, ripple, transform. The Milky Way we see today is just one frame in a very long film, a snapshot of something always in motion. The dinosaurs saw a different galaxy. 66 million years ago, when they last walked the Earth, the Milky Way looked different. The spiral arms were in different positions. The sun was elsewhere in its orbit. The night sky they saw was not the night sky we see. And the night sky of the future will be different still. In a few billion years, the Andromeda collision will begin. The two spirals will merge. The sky will blaze with new star formation. Future generations, if any exist, will look up at a galaxy we can only imagine. The Milky Way is a story in progress. We live in just one chapter. Nothing in the galaxy is truly lost. When a star dies, its matter returns to the interstellar medium, the gas, the dust, the heavy elements forged in its core. This material drifts through space. It mixes with other clouds. It cools, it condenses, and eventually it forms new stars. The iron in a new planet's core may have come from a supernova that exploded 5 billion years ago. The carbon in a newborn star may have cycled through 3 or 4 previous generations of stellar life. The galaxy recycles everything. Matter flows from death to birth again and again, a cosmic circulatory system. And this brings us to something personal. The atoms in your body were forged in stars. The calcium in your bones was created in the heart of a dying star billions of years ago. The iron in your blood came from a supernova. The carbon that forms the backbone of every molecule in your body was fused inside an ancient stellar core. You are not separate from the galaxy. You are made of it. The same processes that shaped the Milky Way shaped you. The same atoms that drift between stars are the atoms you are made of. The galaxy is not something out there. It is something you carry within. And now our journey begins to draw to a close. We have traveled far tonight. From the glowing heart of the galaxy to the quiet edges of the halo, from ancient stars to newborn suns, from the past to the distant future, we have encountered black holes and neutron stars, wandered through stellar nurseries, watched galaxies collide in slow motion, and glimpsed the invisible scaffolding of dark matter that holds everything together. And yet, we have only scratched the surface. The Milky Way contains more than we can ever fully know. Dark matter we cannot see, planets we have not yet found, stars whose light has not yet reached us. Mysteries wrapped in mysteries, questions that will occupy generations yet to come. But that is part of the beauty. The galaxy is not a puzzle to be solved. It is a wonder to be explored. So what have we learned? That the Milky Way is vast beyond imagining. Hundreds of billions of stars spanning 100,000 light years. That it is ancient, nearly as old as the universe itself, a survivor of countless collisions, a builder of heavy elements, a creator of worlds. That it is alive, in a sense, constantly changing, constantly creating, constantly recycling matter and energy, and that we are part of it. You are not an observer looking at the galaxy from outside. You are inside it, made of it, woven into its fabric. Every atom in your body has a history that stretches back to the earliest stars. You are quite literally the galaxy becoming aware of itself. As you drift towards sleep, know this: the galaxy continues to turn. Even now, as your eyes grow heavy, the Milky Way is rotating. Stars are orbiting, gas is flowing, new suns are being born in quiet nurseries you will never see. You are traveling through space at 800,000 kilometers per hour,
carried by the sun on its long, slow orbit around the galactic center. You don't feel it, but it is happening. You are a small, warm point in one of the spiral arms, a flicker of consciousness in a vast, turning wheel of light. And that is a beautiful thing. So let the galaxy carry you gently into sleep. Let the slow, patient turning of the stars be your lullaby. You are safe. You are home. You are exactly where you belong in this vast, ancient, beautiful spiral.
The same stars that shone on ancient civilizations shine on you tonight. The same patterns that guided sailors across dark oceans are waiting above your roof right now. Thank you for joining me tonight. I hope the Milky Way has given you something to dream about. Sweet dreams. You have come a long way tonight, across light years and billions of years, through collisions and quiet pauses, through the bright and the dark. The Milky Way holds far more than we have explored, but for now, this is enough. Close your eyes, let your breathing slow, and know that wherever you drift in your dreams, the stars will still be there when you wake. Thank you for joining me on this journey through the Milky Way galaxy. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the universe. There are more wonders waiting, more galaxies, more stars, more mysteries to drift through on quiet evenings. Rest well, and may the stars keep you company through the night. This has been Drowsy Discovery. Good night.